I'll be talking about this project I have here. It's called What Do Test Scores Miss? The importance of teacher effects on non-test score outcomes. So just as a bit of an overview, the idea behind the paper I think is very straightforward. There's nothing super fancy about it. The basic idea is that the way that we tend to evaluate teachers is by estimating their effects on test scores. And I'm going to argue in this paper and walk you through the argument that there may be a lot of information that we're not taking into account when we use these sorts of measures. Now, this is something that I think a lot of people believe to be true, but I believe this is the first time someone's sort of gone through and dug through data to try and document it rigorously. So by way of motivation, so I think if you sort of ask the question at the broadest level, a quality teacher is a teacher that is able to teach students the skills needed to be productive adults. And I think this is true for an education system in general. The reason we have a public education system is that we think we want to create productive citizens, and by that I mean citizens that are able to hold on a job, citizens that are able to not commit crimes, citizens that are able to vote and just be good citizens generally. But the way in which economists, at least, and many policymakers are sort of moving in this direction, have tried to measure teacher quality is by using what is called value added. So test score value added is essentially a measure of a teacher's effect on test scores, and the idea is as follows. You take a student at the very beginning of the year, and their test score at the very beginning of the year is a good measure of what the student knows at the very beginning of the year. You take their test score at the end of the year. That's going to be a good measure of what the student knows at the end of the year. And the difference between the incoming score and the outgoing score is a measure of what the student has learned over the course of that year. Now, if you were to observe that on average, certain teachers tended to have students who learn a lot more based on this test score growth, you would say that teacher is an effective teacher, and that's essentially what happens here. You sort of do some adjustments for the demographics of the students, but in essence, it's a measure of the average test score growth of students that are exposed to a teacher in a given year, and we call that value added. I should just say, I should have said this before, do you guys typically interrupt? Okay, please interrupt. Yeah, I'm so used to being interrupted before I even get to like point number 3, that if I get through like 2 slides and no one says anything, I feel like I'm bombing. So just give me like a softball in like a couple minutes, just for my own well-being, please. Yeah, so this literature has basically found that on average, having a teacher at the 85th percentile versus the 15th percentile, which is kind of like a 2 standard deviation improvement in terms of test score value added, is associated with about an 8 to 20 percentile points increase in test scores. So these are sort of non-trivial effects. And in a very well-known paper, Chetty, Friedman, and Rokoff, they basically document that teachers who improve test scores, and we sort of call that high value-added teachers, also tend to improve long-run outcomes such as high school completion, college going, and earnings. So many of you are probably familiar with the paper, at least heard of this paper, but what they don't do in this paper is they don't actually estimate teacher effects on long-run outcomes directly. What they do is they estimate teacher effects on test scores and then document the extent to which these effects on test scores predict long-run outcomes. So I think that still leaves open the question, well, what are the effects of teachers on the long-run outcomes, and are there other things, other measures of skills that we could have used that teachers have impacts on that might predict long-run outcomes also? To some extent, we don't really have a good sense of that based on their analysis. I mean, the analysis is very important. So what the analysis did, I think, is demonstrate very convincingly that test scores measure a key set of skills that are important for being successful adults. But what they haven't documented is a whole range of skills that might be important for adult success and what teachers have on those skills. So there's another body of literature out there which has been very sort of up until very recently separate from the teacher quality literature, which is based on non-cognitive skills. So there's a very large body of research that demonstrates that non-cognitive skills that are not captured by standardized tests are very, very important determinants of adult outcomes. So these skills would be things like adaptability, self-restraint, motivation. Lately, there are a whole host of other things people have been talking about, like having a growth mindset. There's also sort of the big 5 that people talk about. And I'll just say I'm using the term non-cognitive here, not because I believe that these are not cognitive processes, but only because I think that's the way they've been referred to in the past. So economists have used the term non-cognitive, so I'm going to follow suit and do the same thing here. But these are, please, yeah. Affective learning. I mean, there's certainly, yeah, I think there are many, many, many things we can call it. I think what you're describing would fall under the same bucket of what I'm calling non-cognitive skills. Mm-hmm. Yes. You know, so I'm well aware of your criticisms, and when you said the problem with, I might say that's one problem with it. But yeah, no, I agree. I don't like the term. I don't love the term myself, but like just in the interest of communication, and because I'm an economist, I'm just going to do what economists do. Um, but being very aware of the fact that, you know, for sure this is not a great label. So I'm just saying, I'm going to use a term, but let's just think about it being broadly associated with things. The term that I tend to use are sort of socio-emotional skills. But I think as long as we all know what we're talking about, we can proceed. But that's, yeah. Yeah, you know, it's just not a fight I'm willing to fight. Like, people can call it what they want, you know? So, yeah. So there are a lot of papers out there that have sort of documented that these socio-emotional skills, soft skills, non-cognitive skills, are highly predictive of long-run success. Some of them have used very high-quality psychometric measures. So there's a study out of Sweden where they basically gathered a lot of, or maybe it's Norway, they gathered a lot of data for men before they go into the armed forces. They're giving a battery of tests to sort of measure things that are going to be predictive of leadership skills and a sort of bravery under fire, basically. And they found that these skills, so everyone basically serves in the military over there. So they basically found that these skills were highly predictive of earnings later on amongst these men. There's also studies by Heckman has many studies on this topic, one of which uses just behaviors and also whether you actually completed high school as measures of non-cognitive skills. And there's a whole host of studies. All of them basically find that these measures of non-cognitive skills are highly predictive of adult success. And I'll show you similar patterns in the data that I'm using as well. So I would argue that this literature gives us reason to suspect that teachers may impact skills that go undetected by test scores, but are nonetheless really important for adult success. There's also evidence outside of the teacher literature that sort of suggests this might be the case. So there's studies on Head Start, for example, where students go to Head Start, they see some initial test score gains, but it goes away, and then you see long-run effects that are pretty big. There's some studies that have looked at the effect of charter schools and have found that individuals who basically are enrolled in charter schools in high school have very small or no test score gains, but when you look later on, they're more likely to go to college, more likely to complete, and very recently there's a paper that came out finding that they actually earn higher wages as well. So there's some sense, so that I think we sort of have a sense that test scores don't measure everything, and that lack of an effect on test scores does not mean there's lack of effect on long-run outcomes either. Yeah. So the key objectives of the paper are as follows. So the first thing I'm going to do, first thing I want to sort of start to do is to extend the value-added model from one where students have a single dimension of ability to one where students have multiple dimensions of ability. And certainly you can think of students could have several different dimensions of ability, but I'm going to talk about two, the cognitive dimension and the non-cognitive dimension. And all the insights from the model basically fall out of moving from a unidimensional model to one where you have more than one dimension. And the key thing is once you move away from this single dimension of ability, then you can have predictions that are sort of different from what you would get if you thought of students either just being high ability or low ability, which is the way the standard value-added model works. And the first prediction is that, you know, teacher effects on multiple short-run outcomes can predict long-run outcomes even if they themselves are not correlated. So this sounds obvious when I say it, but it's actually not obvious if I didn't say it. So the first time I ever presented this paper, I think I talked about the fact that, you know, I'm finding that teachers who have effects on like grades improve long-run outcomes, but teachers who improve grades are not necessarily the ones that improve test scores. And the reaction I got was, well, how is that possible? How could you improve long-run outcomes if you're not improving test scores? basically that statement basically is based on a model where student ability is unidimensional. Either you're good or you're bad. Once you move away from that, there's a possibility that teachers could improve motivation, and motivation could improve long-run outcomes. Teachers can improve cognitive skills, and those cognitive skills could improve long-run outcomes. But teachers who improve cognitive skills do not have to be the same ones that improve motivation. They can be the same teachers. There's no reason why they can't be, but they don't have to be. So once you move away from that, you get a potential disconnect between these two things. The second prediction is that you can actually, if you want to predict teachers or identify those teachers who are going to have large effects on long-run outcomes, you can actually do a much better job of predicting that if you have multiple outcomes, multiple short-run skill measures at your disposal. So you can identify teachers who improve long-run outcomes by using teachers' effects on test scores, as has been demonstrated in previous literature. But I'm arguing if you have teachers' effects on some other measures that are sensitive to, say, non-cognitive skills, then you can get a much better prediction. And that's the other one piece that sort of falls out of the model as well. Then I'm going to basically use a set of non-test score outcomes or behaviors, and I'm going to form basically a proxy for non-cognitive ability. And I'm going to demonstrate the extent to which these behaviors predict adult outcomes conditionally on test scores. And the logic behind this is as follows. So if you observe that you have two students, one had a higher test score than the other, it would be natural to sort of look at these two kids and say, well, the one that has a higher test score probably has higher levels of cognitive skill. Now, of course, there are many other reasons why test scores could be higher than the other one. There could be differences in the family background. There could be differences in just how well they decided to pay attention and taking the test. But on average, you're likely to make the inference that if a kid tends to score better on test scores, it's reasonable to assume they have higher levels of cognitive skill. And we can make the same basic argument for using behaviors. So you might say, well, if there's a student who systematically tends to be absent from class and a student who does not tend to be absent from class on average, it's reasonable to assume that on average, probably the kid who doesn't show up all the time has lower levels of academic engagement, and that would be sort of a measure of lower levels of non-cognitive skill. So the same way you can infer cognitive skill from test scores, I argue you can infer non-cognitive skills from behaviors. So then the third thing I'm going to do is I'm going to basically estimate ninth grade, this is actually not algebra anymore, ninth grade math teacher and ninth grade English teacher effects on test scores and on these non-test score outcomes. So I should also say the version of the paper that you all have seen, I'm in the process of updating it right now. I'm revising it for a journal. So I'm going to show you the newest results, which means two things. One, it means that once in a while the slide will talk about things that some others won't. And it also means that I may be less familiar with actually what the next slide is going to show, because I've only seen it like a day ago. But it's fun. And the results are basically the same, but they're somewhat different. And then the last part is basically I'm going to try to sort of explore how well test score measures and non-test score measures of teacher quality predict their effects on long-run outcomes. So that's basically the game. Yeah.
Why do we only use ninth grade instead of 7th, 8th?
Yeah, it's a good question. So the focus on ninth grade is twofold. One is just sort of data-driven. I needed a grade in which I had good measures of test scores. So the best measures of test scores tend to be in elementary grades, which is why almost all teacher quality papers focus on elementary grades. But in ninth grade, we also do have some pretty good tests because they have standardized tests that are given to ninth graders. So you can estimate teacher effects on test scores in ninth grade. But I also needed to be able to identify teacher effects on behaviors. In the North Carolina data, there was no, so GPA is not collected in high school, for example, in middle school, for example, only in high school. So that's not something I would have had. And also some of the other behaviors are sort of less indicative of skills and lower grades. So for example, some people would argue, which I think is reasonable, when a third grader is absent, that's probably more indicative of what's something going on in the home than the student sort of skipping class. When a ninth grader is absent, it's much more indicative of actions of the student. So that's why ninth grade was sort of the key grade that I looked at. You could ask, why didn't you look at 10th grade? There's no standardized test for most of the 10th grade courses. So it's sort of limited where I could look. I mean,
I don't worry about third grader, but I worry about 8th grader because in my own research I found that the transition year from 8th grade to 9th increases dramatically.
That's probably true.
Yeah.
Yeah. So I think the trend, yeah.
Witness a lot of variation there on eighth grade. Yeah.
So I have absences in 8th grade. That's something I do have, but I don't analyze 8th grade teachers because I don't have good measures in 7th grade. There's another methodological reason, which is that ideally I wanted a context. So in any teacher quality effects paper, you have to be able to make the argument that conditional on some set of observable characteristics, you have to make that assumption. So one of the nice things about 9th grade is that in 9th grade, the students are coming from a different school, so they're not familiar with the teachers in the school. So the likelihood that students are selecting to the teacher who they like or they've heard good things about is much lower than it would be in sort of 8th grade, 7th grade, or so lower grade. So that's another reason why 9th grade is desirable for that reason. Now, I'm not saying that couldn't happen even in 9th grade, but the scope of that kind of behavior, that kind of selection is much less than in lower grades. So from a methodological standpoint, that's also a reason why I do it that way. Does that make sense? Yeah.
In ninth grade, there's many teachers that you can ask. Because one thing I always thought about the elementary school is that one teacher teaches basically everything, and so
Yeah.
that makes things a lot simpler. But so how do you handle the fact that other teachers may influence it?
Yeah, that's a great question. So there are, yeah, I think that is the other reason why people have just steered clear of high school. But it's an important age, and we should try to explore it. So basically, what I'm going to argue is that if you condition on a sufficient set of covariates, then conditional on those covariates, you can make the assumption that teachers are essentially randomly assigned to classrooms. I'll talk about this much more in depth, but it's a very important point, and it's one that I'm going to have to take seriously. So there are a lot of key things to tackle, and that's going to be one of them. So I'll be very clear about the identifying assumptions in the model, and then I'll also show you some empirical evidence that are consistent with the idea that once I control for basically tracking, once I account for the track, then it appears as though there's basically no relationship between the math teacher and the English teacher, which basically allows me on average to identify the effect of the teacher. So but it's a great question, and I do tackle that explicitly in the paper. So, yeah. Okay, so I'll just talk a little bit about the data, and then we'll dive into the model. So the data that I'm using comes from North Carolina. I use all 9th grade public school students in North Carolina between the ages of 2005 and 2012. The student data include demographic characteristics, so that's going to be the gender, ethnicity, and the highest level of parental education. It has transcript data, so I know all the courses that a student took and the grade they earn on that course. The data also include middle school achievement, so their 8th grade test scores prior to entering 9th grade, and end of course scores for math and English, and this is also in 9th grade. I have their suspensions and their absences as well. One thing I'll mention is that the math courses that I use in this paper, in the previous version of the paper that was circulated, I only focus on algebra. In this version, I use algebra, geometry, and algebra 2. So basically, if I used algebra 1, which is the most common course taken in 9th grade, I have coverage of about 60% of students. When I use algebra, geometry, and algebra 2, the coverage goes up to about 90%. It doesn't change the results at all, but it does mean I have a bigger sample size, and the tables are going to be slightly different, but that's a side note. So students are linked to individual teachers via a matching algorithm that I will not go into. And then the data, these 9th grade students' data are linked to dropout outcomes, graduation outcomes, SAT outcomes from the 2005 through 2011 9th grade cohorts. One thing I'll also mention is that I think it's sort of well known that identifying effects on high school graduation and dropout is always a little bit tricky because students who move out of the data, so if you're a transfer student, then you're not going to be coded as a dropout. You're not going to graduate, but you're not coded as dropout, and you have this sort of funkiness in the data. So the nice thing here is that North Carolina does record whether someone is sort of verified to be a dropout, and I'll show you when you see the data, only about 5% of students are actually recorded as being dropouts, which I think is very low. But they also have everyone who's verified to be a graduate. So the nice thing here is that if I only had one of these, then you'd have to worry that, well, if you find effects on graduation but nothing on dropout, we don't know whether it's just like the fact that students are more likely to like leave the district or go to private school or something. But by showing effects on both dropout and graduation that have similar orders of magnitude, you can be relatively confident there's a real thing there. It doesn't have to do with students leaving this, going out of state, going to private school or something else. So like I said, I'm going to limit the analysis to students who took math, algebra 1, geometry, and algebra 2, and English 1. This covers about 94% of all ninth graders, so it's a pretty representative sample. And I'm going to focus only on the first time a student is observed in ninth grade. So the idea behind this choice is that if I were to look at all the observations when our students were in ninth grade, potentially this is endogenous. So if being in ninth grade is a function of the teacher that you're exposed to, then I don't want to look at your observation the second time you're in ninth grade, because that could have been a function of the ninth grade teacher you had the first time around. So what I want to do is focus only on students the first time they're ever in ninth grade, and I'm going to ignore all their subsequent ninth grade observations. So the final data set cover about 573,000 ninth graders in 872 schools in classes with about 5,000 English teachers and then just under 7,000 math teachers. So basically, I'm going to follow a literature in economics, relatively small literature in economics, that basically is going to proxy for soft skills using behaviors. So I'm not going to have psychometric measures of non-cognitive skills. Yeah. Test score. What kind of test score? It's a standardized state test that is given to all students who take Algebra 1 or any of these courses.
And are those tests then, this is through 2011, so these aren't necessarily common core E?
These are not common core tests, no.
Whatever came before from our.
That is correct. Yeah.
Are they substantially different, let's say, from 2005 to 2011? Does this test change, or are they similar?
I have not looked at the raw underlying tests, so I don't know the answer to that question. But it's a good one. So right now, I'm sort of doing the typical economist thing and ignoring measurement entirely. I'm not saying that's the right thing to do, and assuming that, roughly speaking, a standard deviation improvement on a test in 2005 is equivalent to a 1 standard deviation improvement on a test in 2008. But I should, if you believe there may be some changes in the test that took place around that time period, it's something that I could look into. I don't think there's anything I can do about it, but that's something to look into. Yeah. So I'm going to proxy for soft skills using behaviors. So I'm going to use the natural log of absences in ninth grade. I'm going to use whether the student was suspended during ninth grade. I'm going to use ninth grade GPA, and this is going to be across all courses, not only the course that the teacher corresponds to, and whether they were enrolled in 10th grade on time. So I'm going to combine these things to basically create an index. So basically someone on Twitter posted this to me, and I was like, oh, it's amazing. So basically someone pointed out that if you look at grades, retention, attendance, and discipline, then you have like the grad score, and you can use that to predict graduation. So I thought that was pretty awesome, but I thought it was a little bit too cute for me to actually include in the paper, but it's a cool idea. So you can think of it as sort of the grad score. So also, one of the things that's going to come up is I'm going to show you that, if I show you that teachers who improve course grades also are more likely to promote high school graduation, one issue you might raise is maybe this is a mechanical relationship picked due to the fact that some teachers are easy graders, right? So if I'm an easy grader, I give all my kids A's, and somehow if that grade is used to determine whether a student is going to graduate or not, then there's like a mechanical relationship between teachers who raise grades and teachers who promote high school graduation that has nothing to do with underlying skills developed by students. So one way to sort of demonstrate that what I'm showing is not driven by this is I'm going to basically show you that all the results hold up if I use 10th grade GPA as my measure of non-cognitive skills. So basically what I'm going to document is that there are teachers who have effects on 10th grade GPA systematically, and these are 9th grade teachers. So 9th grade teachers are systematically having effects on their students' GPA the following year, and these teachers are different from the teachers who are raising test scores, and these teachers are improving long-run outcomes. And that's to get around this issue of any mechanical effects. Yeah? So I'm being completely agnostic about what's cognitive and what's non-cognitive. So my basic argument here is not, so I haven't shown you the model yet, but my basic argument here is not that, oh, GPA is cognitive and test scores are GPA is non-cognitive, test scores are cognitive. My argument here is that there is information about non-cognitive skills contained in GPA that is not in test scores. So people who, sociologists have written about this in depth. So if you look at the things that determine grades, for example, is a good example. Typically, when teachers assign grades to students, it's based on some measure of achievement, which might be some tests that are given in class or otherwise. It's typically based on some level of perceived effort. It's also based on process. So students who show up on time are not tardy. Sometimes they actually explicitly take off points for being tardy. They'll take off points for not handing in homework assignments. So if you hand in all your homework assignments, you're likely to have a higher grade as well. And you could think being the kind of kid who hands in a homework assignment is more indicative of your academic engagement and these are sort of non-cognitive skills than they are of your ability to score well on some test. So I would argue, and the data actually bear this out, that something like grades is a reflection of both cognitive and non-cognitive skills, whereas test scores are probably a combination of both as well, but test scores, I think, weigh more heavily on the cognitive side than the non-cognitive side. But the arguments that I'm making only require that there is information about non-cognitive skills contained in grades that is not contained in test scores. But I'm not saying that test scores are cognitive and grades are non-cognitive. I'm not making that argument. Does that make sense?
But can't you be doing the opposite? I mean, somebody might argue, look, a teacher knows an awful lot about a kid's skills because she spends all of noon with her. And so the GPA reflects kind of a deep knowledge of a kid's academic skills. Whereas a test score is kind of a noisy, very narrow measure that's partly a measure of, how docile you are, or how your attention span, or how well you can sit still, or how well you follow directions, or a whole bunch of stuff that you might not actually think of as cognitive or academic. And somebody, I think, could have said exactly the same argument you just made, but said the test score is going to contain some non-cognitive skills information that's not contained in the GPA because the GPA is really the better measure of. But it's not obvious to me how you say which is which, because I don't think we have a great definition of what the underlying dimensions of things you have in mind are here.
Yeah.
In fact, the fact that we've just gotten in the habit of using the word cognitive when we talk about test scores and non-cognitive is a bad habit because it acts like we have a good sense of how these dimensions load on these different
Yeah.
kinds of
Yeah.
students. But I think it's kind of dangerous to fall into that because we don't really know what we're doing.
Yeah, so I have two responses to that. One is that I'm basically going to just concede that I'm adopting the tautology that if it's not measured by test scores, it is de facto non-cognitive. So in that sense, what I'm saying has to be true because I'm defining it that way. But your deeper point, I think, is important, which is why do we claim that test scores are a measure of cognitive skill? Maybe they're not, and I think I would argue that maybe they're not. If some, for sure, if you slack off on a test, the kind of person who even pays attention decides to read the test and write down the answers is exhibiting some amount of non-cognitive skills the way that we've defined it. So to think of test scores as being a pure measure of cognitive ability, I think is probably mistaken as well. So I think, and the way that I'm going to describe it here when I show you the model is that students have both dimensions of ability, and every outcome that we observe, every skill measure that we observe in ninth grade is just a reflection of those two things. But they're reflections in those two things to different degrees. So test scores may reflect to a greater extent cognitive skills than GPA, and GPA may reflect to a greater extent non-cognitive skills than test scores. And as long as that's true, that means there's going to be information in one of them that's not contained in the other. So that's sort of where I'm going to stand. So I'm pretty agnostic about what each thing measures, my key, but what I'm going to take a firm stand on is saying that there are skills that are being picked up by these behaviors that are not being picked up by test scores. And I'm going to say that whatever is being picked up by these things that are not being picked up by test scores, I'm labeling non-cognitive, and I'm saying they're important. And there's policy content there.
So I'll buy that, but let me quick give you one step further, and that is because there's measurement error in any test score. If
Yes.
I gave the same student 2 math tests that tried to measure the same set of skills, there's information contained in each score that's not in the other,
Yes.
even though there's only one dimension of stuff being measured.
Yes.
So it seems to me you also have to claim that the fact that you can load on both of them,
Mm-hmm.
not just because they're 2 unreliable measures of the same underlying concept.
Yeah.
Construct, right? You need to convince us that they're more than just measurement error causing.
So I agree, and I'll show you evidence that they're not the same thing. But then, my feeling is I don't know why the default is that people are either awesome or not awesome. Like I find that a strange default position. I think we all know people who are very, very brainy, who just can't get their act together, and we all know people who are just middling in sort of raw processing power, but are extremely successful because they're very motivated and driven to do stuff. So I think anecdotally, we know people like this, but why when it comes to models, we like to just say ability is alpha, it's either high or low. I don't understand why we do that. So I'm not sure that the burden of proof is on me to say that we don't just have one dimension of ability, but I'm going to present some evidence that is, not by no means dispositive, but I'll show you some evidence suggesting that that there's some information in GPA and these other behaviors that seems to be pretty unrelated to test scores. But that's really all I can do. I mean, the key thing is, at the end of the day, we're talking about a dimension of ability that no one can actually observe. So, yeah, I'm not sure if that's a particularly satisfying response, but fair enough. And it's fair. So the reason I think these are reasonable sort of proxies for these soft skills or non-cognitive skills is that if you look at the psychometric literature on these non-cognitive skills, they tend to be pretty strongly related with them. So we know, for example, it's well documented that measures like grit and Big Five and growth mindset are pretty strongly related with things like whether you persist in school, whether you show up to class, whether you act out is also associated with a lot of the Big Five dimensions of personality. So we kind of think they're related. We don't know if they're related, but it's reasonable to think they are the case. And it's also true that these psychometric measures predict these behaviors above and beyond test scores. So it suggests that test scores aren't picking it all up. So then I'm going to basically follow Heckman, Sixrud, and Rizul, and I'm going to use principal components analysis to pull out the first principal component that explains covariance across these behaviors, and I'm going to call that my index, the behavioral factor, and that's going to be my proxy for non-cognitive skills that are included in these behaviors but are not necessarily picked up by test scores. So yeah, I'm going to take this thing, I'm going to standardize it to be mean 0, unit variance, and I'm going to use it the same way we would use test scores. So just as a bit of a side, so if you do this, it turns out this behavioral factor has a correlation of about 0.5 with test scores. So that's a moderate correlation, and if you think about this in regression terms, this implies an R squared of about 0.25. So this is telling us that about 75% of the variation in test scores is unrelated to the behaviors, and 75% of the variation in behaviors is unrelated to test scores. So that, to me, suggests there's a lot of scope for there being some information in there that we're not using when we use test scores. Now, I haven't proven that yet, but it suggests that's the case. The second thing I'm going to do is just ask the question, well, they're not correlated perfectly, not even close to it, and if you were just trying to predict longer run outcomes as a function of these behaviors, do they predict long run outcomes conditional on test scores? So all I've done here in column 1 is I've run a regression using the data of whether a student dropped out of high school as a function of their grades in 9th grade, the natural log of absences in 9th grade, As a technical aside, this is a natural log of absences plus 1 to account for the fact that there's zeros. Whether the student was suspended in 9th grade, whether they made it on time in 10th grade, and then I also include their algebra. In this case, it's going to be their math z-score. This is mislabeled. This should be, I guess, English z-score and then the math z-score. And as you can see, the coefficients on all these behaviors are statistically significantly different from 0, all conditional on test scores. And all the things work in the direction you expect. Individuals who have higher English scores or math scores are less likely to drop out. But it's also true that conditional on test scores, individuals who have higher grades are less likely to drop out. If you're more absent, you're more likely to drop out. If you're suspended, you're more likely to drop out. And if you are basically not attending 10th grade on time, you are, because if you're on time, then you're less likely to drop out. So everything has the sign you expect, and these things are statistically significantly different from 0, conditional on test scores, which is telling us there's information in these behaviors potentially that can explain variation in these long-run outcomes that we care about more than test scores per se. And I should just say that all these models are controlling for a variety of characteristics. So if I were to show this to you without controlling for anything, you might say, well, a lot of this could be driven by differences in socioeconomic status. Individuals who are likely to be absent may come from home backgrounds where they're just predisposed to dropping out anyway. So all these models control for school fixed effects. They control for student gender, ethnicity, parental education, a cubic function of math and reading scores in 7th grade, 8th grade suspensions, 8th grade absences, 8th grade GPA, and whether the student repeated 8th grade. One side note I should say is that when I say that I'm including GPA in 8th grade, this is actually an imperfect covariate. So as I mentioned earlier, because grades are only reported in high school, I only observe 8th grade grades for students who took high school courses while they're in 8th grade. And this happens about 25% of the time. So students might take a math course or some other course while they're in 8th grade. In that case, I have a measure of their grades. It's imperfect, but I still include it as a covariate because it does predict stuff. But one thing I will show you is that all the analysis that I'm presenting here are robust to me excluding GPA as one of my measures entirely, so that everything that I have has a lag control for it. So then over here, this is showing you the same basic analysis using graduation as the outcome. Basically, all the signs are flipped as you'd expect. And then down here, I basically ask the question, well, if we think that all these behaviors, I'm taking all these behaviors and taking an average of that, I'm getting rid of a lot of measurement error to sort of allow for a fair comparison with test scores, so to your point to some extent. I'm going to take the average of the math and reading test scores and use that as my measure of cognitive ability, and we see the same basic patterns. So if you look at them over here, this is telling you that increasing test scores by 1 standard deviation reduces dropout by about 1.3 percentage points, and increasing the behavioral factor by 1 standard deviation reduces dropout by about 5.2 percentage points. This is showing you the same basic analysis for whether you graduate from high school. So one thing that I'll sort of point out, which you're going to see throughout the paper, is that the magnitudes of the test score effects relative to the magnitudes of the behavior effects are quite different. So increasing test scores by 1 standard deviation leads to a 1.8 percentage point increase in graduating high school. The same change, the equivalent change for behaviors is 15 percentage points. So it's a big difference. Now, you still can't, so you can't compare these numbers just yet and say, well, teachers must be more important for this than for that, because I haven't shown you yet how big the teacher effects are in these measures, but it's important, it's helpful just to look at these numbers and see how much larger the marginal effect of a change in this behavioral factor is than test scores. So columns 5, 6, and 7 basically look at a few other outcomes. So this is your high school GPA at graduation. The test scores predict that increasing test scores by 1 standard deviation increases your high school GPA by about 0.15 grade points. The same thing for the behaviors is about 0.35 grade points, about twice the size. Whether you take the SAT, both predict whether you take the SAT, and both predict whether you intend to attend a 4-year college upon graduation. So there's a survey that is given to students at the end of high school graduation, asking them what they're doing next year. And if you say you're going to attend a 4-year college, I include that as one of the key sort of longer run outcomes because it's a very good predictor of whether you go to college. And again, Test scores predict it, but behavior is predicted as well.
Sorry?
Yeah.
Can you go back to the?
Sure.
Can you explain why the sample size changes a little bit from the first two columns to the
Yes.
third?
So these two versus these.
Yes.
So the sample size changes for some of these. So for these, they change because not all the same outcomes are available for everyone.
Yeah.
So you have to graduate to have a GPA. The SAT data are not available in all years, and this survey is not available in 2005. So that's why these sample sizes are different. As for why these are different, that is a good question. My guess is, yeah, I got to double check what that is. It must be something about missing data. Oh, I think that's, yeah. So I think some of these variables are missing. So when I combine the factor, then I think that's the case.
But when you
Yes.
have all those
I know I could tell you. I know I could tell you. Yeah, I think. Yeah. So not everyone has a math score and an English score. So because I include both, you have to have variables. You have to have data for all these variables to be in the data. When I create the average of the two, if you only have one, then that one is in there. So this is basically the average of the two, or one if only one is available. So that's why. Yeah. Yeah.
And I think there's a lot of non-cognitive factors embedded in that fact of what math class they're taking.
Yeah.
Right? So can you talk about how you made that shift? What's going on?
So the empirical fact that I was claiming, just to be clear, is that teachers who improve these behaviors, basically the extent to which that predicts long-run outcomes and the extent to which teachers who improve test scores affect long-run outcomes doesn't change whether I use algebra only or if I use all the students. The key thing is all my analyses are only comparing students who take the same classes. So while it's absolutely true that that Algebra 1 students are different from geometry students, I'm never comparing those kids. All my analyses are made within students who take the same courses. Does that make sense? So that's how I deal with that. Yeah. 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 So it's a good point, and maybe yes or maybe no. So what I'm going to show you, like I said, I'm going to use 10th grade GPA as my measure of non-cognitive skills, and everything is going to be, it's remarkable how similar they are. So that's a sort of indirect way of saying, well, if I use a measure that is not mechanically related to graduation, and is not sort of related to sort of reporting biases or anything like that, we still see the same effect, then it suggests that it's a real thing. But to some extent, you're right. Even there could be some mechanical relationship. The other thing I'll show you is there are other outcomes I look at that are not mechanically related, like whether you take the SAT is not mechanically related to whether you graduate. Whether you say you're going to go to a four-year college is not related to that. So I'll show you things for which there is no mechanical relationship. So I can't rule it out, but for certain, when there is no mechanical relationship, we still see the same pattern results. And I'll show you that. All right. Okay. So this over here is just sort of replicating the same basic analysis using a different data set, just to show you that this is not something specific to North Carolina, but this is something that we see in different data sets as well. So this is using the National Education Longitudinal Survey, 1988. And I basically constructed the behavior factor and a test score factor in exactly the same way and tried to predict dropout, graduation. And in this case, because these data track individuals over time, I have whether they went to college, whether they were arrested, whether they were employed at age 25, and also their earnings at age 25. And you can see consistently across all the outcomes conditional on test scores, these behaviors predict stuff. And this is after you control for ethnicity, gender, family income, family size, and school. So there's something there. The other thing I'm going to show you is to, again, make the argument these are real and these are actually picking up underlying non-cognitive skills, is to basically show you that these non-cognitive skills behave the same way psychometric measures of non-cognitive skills behave in predicting earnings. So here's the fact. If you look at the data using very rich psychometric measures of non-cognitive skills, the finding is that these non-cognitive skills matter a lot at the lower end of the earnings distribution than do cognitive skills. And that as you go up to the higher end of the earnings distribution, cognitive skills matter more. The basic idea is that for jobs at the lower end of the earnings distribution, it's really important that you like show up and aren't rude to your boss and behave yourself. And that's different from like up at the other end. When you get to the upper end of the distribution, perhaps those behaviors are less important. And what's more important is that you sort of can sort of think hard and solve complex stuff. And so that's been a general finding. So I'm basically going to show you the same pattern when I use this behavioral factor in predicting earnings. So what I've done here is I've run a unconditional quantile regression where I'm basically regressing earnings at the 25th percentile of the distribution, the median, the 75th percentile, and the 90th percentile. And as you can see here, at the 25th percentile of the distribution, test scores actually have almost no effect on earnings at the 25th percentile. And these behaviors have a very, very big effect. This is basically telling you that increasing a behavioral factor by 1 standard deviation increases earnings by 23% at the 25th percentile. And as you go up the earnings distribution, you see the coefficient on non-cognitive stuff go down and the coefficient for the cognitive piece go up. So this is sort of mimicking the exact same behaviors that we observe using psychometric measures, suggesting that these are real things. And they perhaps are picking up the same basic concepts. Okay, so now for the theoretical framework. So the theoretical framework is as follows. So students, how am I doing on time, by the way? Yes. Yes. No, you're good. Mm-hmm. So everything you're saying is perfectly consistent with the story that I'm telling, I believe. Yeah, but that would explain. Yeah. Right. Yeah, I mean, so that was I was speculating as to why this may be important here, but you're right. It could be something about school quality. That's right. Now, obviously, that would not explain the result over here because it goes in the opposite direction. But it would explain the increasing importance of cognitive skills in the upper end of the distribution. That's right. So the basic model is as follows. So every student I is going to have 2 dimensions of ability. They have ability in the cognitive dimension, which is, has a subscript C, and the non-cognitive dimension, which has a subscript N. Teachers have an ability vector omega, so each teacher J. And basically this ability vector describes their ability to increase student skills in each dimension. So this is not talking about this teacher's own cognitive ability or the teacher's own non-cognitive ability. What I'm talking about here is, so a teacher who's high on the cognitive dimension is a teacher who is able to increase students' cognitive skills. A teacher who is high on the non-cognitive dimension is a teacher who is able to promote students' non-cognitive skills. So I'm defining teacher ability by how they affect students. So in the model, to make things simple, you can think of the total ability of the student at the end of the year as being the sum of the two. So this ability vector alpha is a vector with a two-dimensional vector, and it's basically the incoming ability plus the contribution of the teacher to each dimension of ability. So here, each outcome that we observe for a student is going to be a linear function of the student's ability. And you can write it as such. So we have the outcome y is basically the ability vector multiplied by a set of weights. So these weights basically are saying, so if my outcome y, for example, is test scores, and I'm just going to say theoretically, if hypothetically speaking, test scores are only a function of cognitive skills and not non-cognitive skills, then the beta that we multiply by the cognitive piece will be large, and the beta that we multiply by the non-cognitive piece would be 0. So this vector of betas that we're multiplying by the ability vector is just a way to talk about how abilities map into outcomes. And the betas are going to be different for every different outcome. So over here, this is to address your point about other teachers. Because students are basically in, well, they're 9th grade, they're exposed to many teachers, we have to think about the fact that total ability at the end of the year, or total outcomes at the end of the year, are going to be a function of the incoming ability, the contribution of their own teacher, but also the contribution of other teachers as well. So that has to be incorporated explicitly into the model. And that sums up to the overall ability, which is multiplied by this beta vector here. So in this model, the difference in student outcomes between teacher J and the outcomes with an average teacher is going to be a measure of the teacher's effect, essentially the value added. And you can see very clearly from the model, if you multiply this all out, all that is the teacher piece multiplied by the weights. So this piece here is the effect of teacher J on outcome Z. So the teacher J's outcome, so the teacher J's effect on the long run outcome is basically also going to be a weighted average of her effect on each dimension of ability, where each dimension where the weights are not equal to 0. So the key sort of insight, or the key sort of takeaway from this slide, is that the same set of teacher abilities that determine their effects on test scores or attendance or grades are the same ones that determine the teacher's effect on long-run outcomes. And that's going to be key. So the next slide is basically going to argue that if that's the case, then we can use information in the teacher effects on each of them to figure out what's going to happen to the long-run outcomes. So everyone sort of got the model? Yeah, okay. So the proposition here is that one can predict a greater fraction of the variability in teacher effects on the long-run outcomes using 2 short-run outcomes that reflect a different mix of both ability types than using any single one alone. So if I want to predict the teacher's effects on earnings, I'm going to do a better job by using the teacher's effects on test scores and the teacher's effect on GPA than on using teacher effects on test scores alone. And the math behind it is, like, I'll just go through very quickly, is as follows. So basically, you could think of it as this. So if you regress the teacher's effects on the long-run outcome on her effect on outcome 1, we'll call it test scores, then the residual, that piece that's left over, is going to basically reflect the dimensions of ability that are reflected in the long-run outcome that are not reflected in test scores. And if you write that all out from the model, you find that it's basically, you can write it like this. And it's a function of omega, which is the teacher's ability vector. Now you can do the same thing. So this is the variability of the teacher's effect on earnings that is not picked up by her effect on test scores. You can do the same thing. So if you regress the teacher's effect on some other short-run outcome, call it GPA, on her effect on test scores, then whatever's left over is also a function of that same ability vector. So this is the variability in the teacher's effect on GPA that's not explained by her effects on test scores. Now, mathematically, when you look at these two things, they're both functions of exactly the same parameters. So what this is telling you is that in this model, these two things must be correlated. And if they're correlated, that means that we're explaining more of the variation in the long-run outcome by using both. So that's basically the math of how this works out. For the long-run outcome, that's right. That's right. That's correct. That's correct. So I would argue that you can, for sure, you can say so. It's possible that there may be some long-run outcome that is only a function of non-cognitive skills, in which case this will break down. Or it's possible to find an outcome where it's only a function of cognitive skills, it will break down. But there are many outcomes. So you might think of the policymaker as thinking of, well, I want to know the teachers that are going to reduce crime. And we might say, well, crime is really a function of non-cognitive skills. And you might say, well, I want to find the teachers that are good at increasing college going, and maybe college going is a function of both. And someone else might want to care about unemployment, and unemployment may be a function of so you can sort of vary this out. But this is basically telling you, aside from the trivial case where either the same exact weights that determine test scores are the ones that determine the long-run outcome, or which is analogous to saying that the weighted base is equal to 0. Aside from those trivial cases, this is almost always going to be true. Like mathematically, that's going to be the case. Okay, so now I'm just going to derive an empirical model from the theoretical model. So very quickly, I'm going to basically introduce some randomness to these 9th grade skill measures. And I'm going to say each 9th grade skill measure, 9th grade outcome, for student I with teacher J is going to be a linear function of student ability at the end of 9th grade plus a random error. So it's going to look like that. So this is the same term as we had before, but now I'm adding some random error to it. So if you basically cross multiply out the first terms and substitute in the effect of the teacher, what you get is that the outcome is a function of the teacher's contribution to that outcome plus all this stuff. And all this stuff, basically, you can think about what that is. All that stuff basically is incoming ability and the contribution of other teachers. So when you sort of take the model and when you take the theoretical model and bring it down into an empirical model, it's pretty clear what the identifying assumptions have to be. So in any OLS model, in order for us to be able to reliably identify theta j sub z, it has to be the case that teacher equality is unrelated to the error term. In this case, that basically means that teacher equality must be unrelated to the incoming ability of students. This is kind of like a no sorting condition, which I think is standard. And the second one is that the teacher quality must be uncorrelated to the quality of other teachers. So it can't be the case that the math teacher quality is indicative of the English teacher effects, because then that would be a problem. And then you couldn't pull those two things out. If every single time you saw a math teacher that was really good at raising non-cognitive skills, they also had an English teacher who was good at raising non-cognitive skills, i.e. a positive correlation, then you could never pull those two things apart. But if the ability of the teacher in math was unrelated to the ability of teacher in English, then you can identify this effect. And those are the two identifying assumptions that I have to show you are satisfied. So, like I said before, identifying assumption 1 is conditional random assignment of students to teachers. This is just saying that. So conditional on some set of controls, the relative effectiveness of teacher J is uninformative about the expected incoming ability of students in class with teacher J. The second assumption is conditional independence of teacher effects, which is to say that conditional on some set of control variables T, the relative effectiveness of teacher J is uninformative about the relative effectiveness of the other teachers of students in class with teacher J. So knowing that your math teacher is really awesome tells me nothing about how good your English teacher is conditional on these covariates. That's the assumption.
You're talking a lot about teachers, and I'm thinking about students and the effect of peers, especially
So pairs are going to matter. So all the models are going to include controls for pair characteristics and classroom averages of the lag characteristics to account for that. So I'm essentially abstracting away from that. I'm not saying it's not important, but I'm essentially abstracting away from that and focusing on the piece that is specific to the teacher. But I do control for that explicitly in the models. Yeah. Okay, so how do I estimate these effects? So I'm going to follow the standard convention in the value-added models. I'm going to say that the outcome is a function of observables plus an error term. And here, xit, this matrix, is going to basically denote all the observable student and class characteristics that is going to hopefully account for tracking, sorting, incongruability, and hopefully conditioned on all these variables, my two identifying assumptions are satisfied. So the sorting variables are as follows. So I'm going to control for incoming outcomes. So I have math and reading scores in both 7th grade and 8th grade. I have repeater status in 8th grade, whether you are suspended in 8th grade, your GPA in 8th grade with the caveats I've already mentioned about that, and attendance in 8th grade. I include student level demographics. I have their parental education, ethnicity, and gender. And that's to hopefully account for sorting of students, then to account for tracking. I'm going to include classroom averages of these same lagged outcomes I just described. This is essentially control for pair effects. And I'm also going to include here the number of honors courses taken during 9th grade, school by year fixed effects. So I have a fixed effect for every school in every year. This is going to help account for the fact that maybe there's an awesome guidance counselor that comes in that drives down attendance in that year, or drives up attendance in that year. And for all classes, so a school by year fixed effect is going to account for that. And then the last variable is going to be indicator variables for each track. So the track variable is actually really important. It's going to be doing a lot of work for me here. So the track variable is the unique combination of the 10 academic courses that 9th grade students take. So this would be like Algebra 1, Geometry, Biology, the social science, physics, et cetera. So you have these 10 courses that everyone takes. I'm going to take the unique combination of those 10 courses at the school as my measure of track. And I'm also going to account for the level at which the students take math and English. So what that means is when I conditional on track, I'm only comparing students who took exactly the same courses while in 9th grade at the same school and took math at the same level and took English at the same level. And by the same level, I mean remedial, honors, or regular. So it's a pretty fine-tuned measure of the kinds of courses that individuals are taking. And importantly, this is defined differently for every single school. So if you're in a different school, you're in a different track. If you're in the same school, but you took one course differently from somebody else, you're in a different track. If you took the same courses, but you took honors math and I took remedial math, we're in different tracks. So I'm only making comparisons among students who took exactly the same courses at the same school at the same level. And this is going to be my key conditioning variable.
So do you have school by year by track effects? Or
I do not have that.
so it's not quite exactly the same. You're not only comparing.
Yeah, so it's school. No, it's school by track, but it's not school by year by track.
Oh, it's school by track and school by year.
Yes,
Oh, okay.
right. But I'm not doing school by year by track. So you can. So if you So to clarify this question, if you take two students who take the same courses at the same school but in different years, they are in the same track. The reason for that is a lot of variation could occur because if you only have one algebra teacher, and they change over time, I want to exploit that variation. If I include a year effect in there, then it kills it. But yeah. So, okay. So, and just to be clear, so the rationale behind this is that, it's plausible that students might select, that teachers might select the schools such that on average many schools may have great math teachers and great English teachers. And it's also plausible that maybe the stronger math teachers select to teach the honors kids and the stronger English teachers select to teach the honors kids. But I'm making the assumption or the argument that conditional on teaching the same sets of kids, it's all the same. So maybe the teachers do select into the honors track, But once you get into the honors track, it's kind of random what students you get. So I'm controlling for the level at which the selection presumably takes place. Yeah. So the way that the model deals with that is it accounts for the level, but it keeps the teacher the same. So it doesn't. So like I don't separate out those teachers in the data. So like in other words, I don't treat me with my honors students as being a different person from me with my regular students. What I do is I say I'm the same teacher. I teach honors kids and non-honors kids, and I'm going to account for the honors kids course, but I'm going to allow me to be the same teacher. So so the model does not. So I don't identify a separate effect for the different sets of kids. It's the same teacher. Does that make sense? Yeah. But for sure, and this is going to come up especially when for like algebra. For sure, some teachers teach algebra 1 and algebra 2, and in that case, all her students are going to contribute to her teacher fixed effect. But I'm controlling for the level at which they take algebra in the models to account for any differences. Yeah. But I mean, the question you're asking is an interesting one, but one that I haven't tackled here, I believe, which is, if I'm good at teaching algebra 1 students, am I good at teaching algebra 2 students? Or geometry?
Yeah, or right. So am I naturally a better teacher?
Yeah.
With my honors kids than I am with my quote-unquote regulars?
Yeah, I've basically not allowed that to happen in the data. Yeah, but it's a good question. And I think the evidence I've seen on this suggests that it could in fact be the case that teachers are differentially good. Yeah. So the residual piece here basically is comprised, so if you estimate this model and you control for all the x's, all the covariates, what's left over, the residual is comprised of the teacher effect, a classroom effect, and a student effect. So these two things are sort of random error terms, and the average of these student level residuals for a given teacher, I'm going to call it E upper bar, is going to be an unbiased estimate of the teacher's effect on outcome Z. Pretty straightforward. But to avoid bias, that could be mechanical, I'm not going to use, so this is perfectly fine if I took the average residual for a teacher and said that's the effect of the teacher. That's perfectly fine if that's all I wanted to do. But if my objective is to use this to predict some other outcome, I can't use this and regress this on high school graduation, because that's going to lead to mechanical bias. If there were some kids who, for some unobserved reason, happen to be awesome and drive up the teacher's average residual, it's also the same sets of kids that are going to drive up the average graduation rates. So that's going to be a problem. So instead, what I'm going to do is I'm going to say, forget about using the own students to estimate the effect of teachers. I'm only going to use the effect of the teachers using all other years of data. So I'm never going to be using the same sets of kids whose outcomes I'm analyzing in the long run when I'm talking about the effect of their teachers on test scores or behaviors. So I'm going to basically use a sort of a leave-out mean. So I'm going to use the average residuals of the teacher for all other years as my measure. And then the last thing I'm going to do is I'm going to adjust each teacher's estimate for estimation error and create empirical Bayes predictors like this. So essentially, what the empirical Bayes estimation does is it takes what is an unbiased estimate of the teacher's effect and turns it into the best predictor of the teacher's effect. So what it's doing is it's saying, okay, well, there's some teachers for whom we know we have a lot of data, and if you have a lot of data, then your average residual for that teacher is probably pretty reliable. And in that case, you don't do much to the teacher effect. But there's some teachers who may have like 3 or 4 students for whom the average residuals based on 3 or 4 students is unreliable. They could have had a different level. They could have had a different average residual in a different year just by sampling variability alone. So we know that's an unreliable estimate. So in that case, what we would do is we would take that teacher and we would basically shrink that teacher's raw estimate towards the grand mean to account for the fact that some teachers have noisier estimates than others. So we basically multiply the raw leave-out estimate by a signal-to-noise ratio. So the logic behind this, very, very simply, is as follows. If you are trying to predict out of sample the outcome of a student based on the teacher's estimate, you'd run a regression. And the regression would be have some intercept and a slope. So you say, what's my best guess of the outcome of or what's the best of the student's test scores, let's say, as a function of the teacher's value added in other years. And it's pretty, you can basically crank out the math, and what you're going to find is that the coefficient on the teacher value added is going to be less than 1. The reason it's less than 1 is when you run a regression, the slope is covariance over the variance, right? So the covariance between the outcome and the teacher effect is going to be the teacher effect divided by the variance of x. In this case, x is a measured thing, and it has noise, which means that basically we have the variance of the truth divided by the variance of the noise. And because, variance of the estimate. And because the estimate is truth plus noise, this thing must be less than 1. So this is telling you that if you want to predict outcomes out of sample, you want to shrink this thing towards some grand mean. In this example, it happens to be 0. So that's sort of the rationale for using empirical Bayes as opposed to just using the raw estimate itself. Okay, so here, this is the first thing, just showing you the magnitudes. How am I doing on time, by the way? Wow, okay. So if you look at the magnitudes of the effects, I'm just going to skip over this. So here, if you take the estimated effects and ask how correlated are they, I've estimated effects on all these individual behaviors and test scores and looked at the correlations. And the first thing here you see is that the correlation between the teacher's effects on behaviors and the teacher effect on test scores is about 0.22. So it's pretty low. This is an R squared of less than about 5%. So 5% of the variability in test scores is related to variability in the effect on behaviors. If you looked at the effect on 10th grade GPA, the correlation is 0.122, which is an R squared of less than 2%. So they're not very strongly correlated at all. Now you might say, well, these are noisy measures, so the low correlations may simply reflect that these things are noisy. So to get a sense of that, what I did is I'm going to estimate a model where I'm going to predict the test scores as a function of the out-of-sample test score effects and the out-of-sample effects on behaviors, and ask whether teachers who improve test scores out of sample improve test scores in sample, and whether test scores who improve behaviors out of sample improve test scores. I'm going to do the same thing for behaviors. And one sort of minor technical point, I'm going to rescale everything so that the coefficient on the teacher effect is going to be interpreted as the effect of increasing teacher quality for that outcome by 1 standard deviation. So this is showing you here that if you increase 9th grade teacher's test score value added by 1 standard deviation, her test scores go up by about 6.8% of a standard deviation. The other thing I'll just point out, so if you predict behaviors, as you'd expect, teachers who predict behaviors out of sample improve behaviors in sample. So increasing the behaviors value added by 1 standard deviation increases behaviors by about 5.7% of a standard deviation. Similar patterns for 10th grade GPA. I think the other interesting pattern here is that if you try to predict 9th grade test scores, 9th grade test scores are conditional on the teacher's test score effect. Conditional on teacher's test score effect, the teacher's effect on behavior is basically unrelated to test scores. And in this case, the coefficient is actually negative and is marginally significant. So this is kind of telling us that insofar as these things are related, once you control for test scores, the behaviors are just not predicting improved test scores, but they do predict improved behaviors even conditional on test scores. So that I take as evidence that whatever is in these behaviors that's not picked up by test scores has to do with behaviors and does not have to do with test scores, which to me says they're different things. And it's not just a question of measurement error. I don't know if you agree, Sean, but that's sort of my interpretation of these patterns. So now let's just look at the outcomes. So now I'm running exactly the same models, but now my outcomes are whether you graduated from high school and whether you dropped out of high school. So column 1 is saying that, and this is a linear probability model, that if you increase 9th grade test scores, a 1 standard deviation increase in teacher quality for test scores increases the likelihood of graduating high school by 0.15%. If you include the teacher's effect on behaviors, the coefficient goes down a little bit, which is not surprising because they're not very highly correlated. And the coefficient on the teacher effect on behaviors is 0.0147, which is saying that if you increase the teacher's effect on behaviors by 1 standard deviation, you increase the likelihood of graduating high school by 1.46 percentage points. Now, it's helpful to sort of think through what the point estimates would look like if you just took the correlations I showed you in the beginning, multiplied them by the size of the teacher effect. It turns out if you do that, these numbers are almost exactly these. These line up almost perfectly. So this is sort of in the ballpark of what you'd expect based on the raw correlations in the data. The other thing I did here is just to get a sense of, so first this is telling you behaviors predict high school graduation above and beyond the effect on test scores. And the question is, how much more variance can I explain? So what I did here is I took the fitted values from this regression based on the test score value added. I took the fitted values of this regression based on the test score value added and the behaviors value added, and computed the variance of each one, and computed how much the variance increased based on including teachers' effect on behaviors. And as you can see here, the explained variance at the teacher level goes up by about 300%. So we can explain a lot more of the teacher's impact on high school graduation by including her effect on behaviors than using test scores alone. Over here, this is showing you a similar model. Columns 4 and 5 are now using conditional logit models to account for the fact that the outcome is binary. And everything is pretty much the same, but the one thing I'll point out is that the implied marginal effects are larger. So I'll just point your attention to over here. This is telling you that increasing teacher quality on the behaviors dimension is associated with a 3.3 percentage point increase in high school graduation. And to show you that this is not a mechanical effect, I did exactly the same thing using the teacher's effect on 10th grade GPA. And here you can see that increasing the teacher's effect on 10th grade GPA is associated with being 3.7 percentage points more likely to graduate from high school. These two numbers are almost identical. So this is telling you that it's not a mechanical thing driven by reporting bias. It's potentially a real increase in skills. These columns are showing you the same thing for dropout. The patterns are similar, so I'll just skip over that. Yes?
So if we just look at the linear model, how different are the R-squared? Maybe this is a bit how I want to know the R-squared.
So the R-squared in these models are hard to interpret because they have so many fixed effects in there. So I don't know. So I didn't even look at it. So instead, what I look at is this. For test scores, it's shrunk probably about as a third, which I think is typical. A third of it is signal, which is typical. I think for the behaviors, it's much lower. For behaviors, I think it's like maybe 10% is signal. So there's more shrinkage going on in the behaviors than for the test scores. But just to keep in mind, I'm not showing you z-scores here of the estimated effects. That's not what I'm showing you here. What I'm showing you is a rescaling so that a rescaling based on this model such that this coefficient is exactly equal to the underlying covariance across classrooms. So this is accounting for the measurement error, basically. Because of time, I did not show you that one slide, but that's what's going on here. So I've got like 5 minutes by my estimation. Is that right? So yeah, 8. Okay. So yeah. So this is just showing you the same basic patterns using a few different outcomes, sort of intermediate. So I do the same thing. I do the same thing here for so whether you predict whether you're enrolled in 10th grade. Again, obviously, whether you're enrolled in 10th grade is basically part of the 9th grade behaviors. But the bottom line is this is an important outcome, and it's not picked up by test scores, right? So whether you're enrolled in 10th grade, you can explain 800% more of the variability of the teacher's effect on that by including behaviors. Looking at 10th grade GPA, you can explain 33% more of the variation with the behaviors. For high school dropout, 326% increase in the explained variance. High school dropout, I've already talked about that. The column 5 is whether you take the SAT. And again, this is nice because this is not something that is mechanically related to any of the other stuff. Whether you take the SAT, you increase the variance by about 226%. Your SAT score, nothing. SAT score, behaviors don't explain that. Test scores do. Not surprisingly. So I'm saying, do test scores predict test scores? Yes. But do behaviors predict test scores? No. And that's consistent with the previous stuff as well. Whether you intend to attend a 4-year college, you increase the explained variance by about 182%. And then your GPA in 12th grade, you increase that by about 607%. So all these measures that we think are pretty good leading indicators of successful outcomes later on in life, you can explain a lot more of a teacher's effect on these things by including her effect on behaviors versus including test scores alone. Same basic analysis using the teacher's effect on 10th grade GPA, and the same basic pattern pertains, so I'm not going to talk about that. But you can see stars where you expect to see stars, and point estimates are there. Last thing I'll say is I did do an analysis by subject. This time around, the differences by subject are a lot less stark. Sometimes we see differences by subject, sometimes we don't, between math and English. Just to see whether, so in many cases, the point estimates are different, but I actually ran a test to see, okay, what is it, test whether the coefficient on behaviors for English teachers is different from the coefficient for math teachers. And actually, in most cases, the p-values are pretty big. So that's what you see down here. These p-values are like 0.7, 0.3, 0.2, 0.7. So I take this to mean, look, it appears as though on average, the non-cognitive piece, the behaviors are more important for English teachers. That's definitely true, but it's not a finding that is robust enough for me to really say is a strong finding, but it's suggestive. And this is sort of interesting because if you go back to sort of the Chetty et al. Paper, what they basically find is that English teachers have bigger effects on long-run outcomes, even though their effects on test scores are actually kind of small. And this would be sort of this would be consistent with the story. If the teachers who are improving test scores are also ones who are improving non-cognitive skills, and this is larger for English teachers, as I'm documenting here, that could explain the pattern of results that they have as well. But again, this is kind of suggestive. Okay, so to test the identifying assumption that there's no sorting, I do two things. The first is I basically create predicted outcomes based on all the 7th grade variables and demographics, and then I regress the estimated teacher effect on predicted outcomes. I find that there's no relationship there. The second thing I do is I'm going to basically instrument for the teacher that you have using the average quality of the teachers in the school at the same time. The key thing about doing that is by using the average for the entire cohort, you're automatically eliminating any selection that may be going on within a cohort. So if an entire cohort does better, when the average estimated effect of teachers in those cohort goes up, it cannot be due to the fact that teacher A is getting the better students in the cohort versus the other, because we're not comparing anyone within cohorts anymore. We're only comparing across cohorts. And using that strategy, I realize I'm going a little fast. Basically, I find the results are basically the same. And I also include school-specific linear trends in these models to account for the fact that some schools may be getting better or worse over time. Very quickly, I'll just say that to show that there's no confounding effect of other teachers, the first thing I do is I basically took the data, took the math teachers and the English teachers and asked if they're correlated with each other. All these in green are the correlations between the math teacher effect and the English teacher effect, the estimate effect. And as you can see, they're all surprisingly small. But you might say, well, these things are noisy, so maybe that's what's going on. So the second thing I do is I actually estimate all the models where I include a fixed effect for the other teacher. So for all the math teachers, I include the fixed effect for the English teacher, and for the English teacher, I include the fixed effect for the math teacher, and those effects are almost identical. It doesn't change anything. So that suggests, what this is sort of telling us, that the effects of the teachers are unrelated, such that I'm identifying the effect of the teacher from that of other teachers in the cohort, in the track. So, yeah, so this is, yeah, same thing. Okay, so is this due to a mechanical effect? I'm going to say no. I've already talked about this quite a bit. Many outcomes are not mechanically related to these outcomes, to the 9th grade outcomes, so that suggests it's not the case. Using 10th grade outcomes does improve out. Using 10th grade GPA, the results are the same, so it suggests that that is not what is going on there. One question would be, Well, you don't have a perfect control for GPA. So if you're using GPA as your skill measure, but you're not controlling for GPA, that's going to be a problem. So over here, I've actually created the behavioral factor without using GPA. And as you can see, the coefficient here is big and statistically significant in predicting high school graduation. And in fact, I actually estimated effects for each one of these individual 9th grade skill measures. And many of these, they all have the right sign, and some of them are significant. So absences alone predicts it. GPA, which is consistent with what you found. GPA alone predicts it. Whether you're on time in 10th grade predicts it alone. So, and then GPA in 10th grade, of course, predicts it. So this appears to be a real thing. As I said, nothing's dispositive, but all the results and robustness checks suggest that this is not driven by selection or an inability to control properly for GPA. Last thing I'll say very quickly, there's a lot of numbers here, but the punchline is pretty straightforward. If you try and find observable teacher characteristics that predict their effects on behaviors, basically nothing predicts it. There you go. So this is kind of not dissimilar from what people have found using when they try and predict teachers that improve test scores. So the only thing which systematically tends to be associated tends to be like years of experience. Sometimes if you have good measures, maybe school selectivity. So some of these things do predict test scores, but they're relatively weak, which is why people are so excited about value added to begin with. So this is kind of similar in that vein. Observed teacher characteristics do not appear to explain teachers' effect on these behaviors. I don't know. So last thing I'll just sort of end on is say, well, what can we use this for policy at all? So I think it does appear that using the observed characteristics I talked about are going to be sort of limited for teacher hiring, but I think there are ways we can do it. So, one other thought would be, well, let's incentivize teachers to improve these behaviors, but that also is pretty undesirable because some of these behaviors can be easily manipulated. So if I'm going to get a raise, if I increase the grades of my students, suddenly all my students are going to get A's and they're not going to learn anything. So that's not going to be a good idea. So one thing you could do is, you could observe behaviors that are correlated with these behaviors. I'm going to say, sorry, you should observe teacher behaviors, like teacher practices, that are correlated with these behaviors, and you can incentivize those. You could come up with, other measures of soft skills that are much more difficult to game, and you could incentivize those. Another way you can do it is you could actually incentivize behaviors in the following year. I've already documented that 10th grade GPA is a valid measure, so we can incentivize that. That's another outcome. So I think there are ways we could use this for policy, but I actually don't take this paper as being one that's going to say, well, this is the policy you should pursue. I see this paper as being more of opening the conversation about how we should think a little bit more broadly about how we identify teacher effects. And I think this relates not only to teachers, but human capital interventions more broadly. Educational interventions, we oftentimes evaluate them using test scores, and I'm going to argue that this is probably an undesirable thing to do because there's a lot that you're potentially going to miss. The data basically say there are 2 dimensions. So to be clear, I never did that here. Here I just sort of said, look, test scores are test scores and behaviors are behaviors, and I'm not making any underlying assumption about what the correlations across these things may be, so I'm being pretty flexible about it. But having said that, if you were to throw in test scores and behaviors in a model, you will find that they do separate into these 2 different things. And the weights on this, well, actually 3. So the test scores load together, the attendance and discipline and absences load together, and GPA loads on both, which is exactly consistent with the way that we think about it. We think of behaviors, we think of grades as being kind of a combination of cognitive ability and non-cognitive ability. We think of absences and discipline to be more of a non-cognitive ability type thing, and test scores being more cognitive, and that's precisely what a basic or sort of principal component analysis is going to tell you. Yeah. So I think old version of this paper had that in there, but this has been taken out. Yeah.